Okay, so today I'm going to talk about three of the harder problems in the East Central Regional. Now there are, apart from the five problems that I talked about before, there are five other problems in the contest, and I'm not going to talk about the first one, Bubbly Troubly, or the last one, Yes, Yes, it's a nonogram, because they are probably is substantially harder, and probably in this region, if you can do the other eight, you would probably be the top three. So if you want to look at those two, feel free, and we can discuss about it. But I would say that A and J are significantly harder. So I want to talk about the remaining three. So even in the East Central, which produced probably, which is probably one of the harder regions in North America. If you stop the eight problems, you could be in top 10, and you'll be tied with Waterloo and U of T and Carnegie Mellon and so on. All right, so I'm going to skip A and J, but I want to talk about the other three. So let's start from the first one. So I'm not going to really say too much about the problem description. I'm going to assume that it's by this time. If you're interested in these problems, you have already read the problem. So I'll just kind of jump straight to it. Basically, the problem is that you have the ASCII art that always contains two regions, one that's called A and one that's called B. The regions are always connected by up, down, left, right, and A and B always intersect, and they're only always intersect in two different places, and the intersections are always in a X, like in a vertical X like this. So here, it will always intersect in this way. And in this loop, you're not allowed to touch, the loops are not allowed to touch itself. So everything is very um, well specified, and you don't have to worry about too many cases. And the question is, you have to figure out how many of these dots are completely within the A loop, how many of these dots are completely within the B loop, and how many of them are intersect. Okay, so this is basically a Venn diagram. You have to figure out how many are in A, not B, how many are in B, not A, and how many of them are in both A and B. So here's another bigger example where this A is the shape of A is a little bit funnier. And so this is so can I control this? Why am I not drawing it? With let's see if I can draw this time. No. Okay. This works. Oh, I can draw it with my mouse, but not my tablet. Okay, so anyway, the A loop goes like this. And then the B loop, let me change the color, goes like this. And then when you're tracing a loop, it always goes in the four directions. There are only four directions you can go. And then when you cross into another loop, it's always an X across. Okay, so you always go straight across. And then based on that, you have to figure out that there are 21 dots that's just in A and not B, 22 dots that are in B but not A, and then 10 of them are in common. Okay, so that's the idea. That's the question. And how big is this? At most 100 by 100. Okay, so it's actually not that big in the grand scheme of things, and we just have to basically do it. All right. So what are we going to do? Why is my pen not working at all? So here we are. No. Yeah. Oh, I have to press the button for some reason. Why do I have a press button? Never had to press the button before. All right. Okay, so let's fine. I'll press the button. All right. So you're gonna have your grid, and then you're gonna have a bunch of x's that trace out the region, and one of these x's will be an A or a B. So let's just simplify things and just pretend that there's only one region for now. How do we trace it? Well, first you look for the A. So you look for the A. It's fairly easy. You just look through and find where the A is. And then you just basically look for every A, you look for one of the four neighbors, and one of them, at least one of them, will be an A. Okay. So sorry, an X. So you look at one of the four directions. You pick whichever one. In the first case, there's two, and you just change it to an A. Okay. Now that you've changed these two to an A, when you look for neighbors again, there's only one X here because the other one has already been changed, and you just follow along, and eventually you would change all of these things to A, and then when you don't see any more X's around you, then you know that you have to basically identify this whole region. Okay, so you basically just have to trace, and you can do it in different ways. You can do a loop while wherever you are, you have some current position, then you find your A, then you look for the four neighbors while you can find an X, go there, and then update your change it from X to A, update your position, and just keep going until you're done. And you can do the same thing with B. But the problem is, what if you have a B here, or whatever shape it is. Now you're told that when you intersect, it's always going to be intersecting in across. So the intersection points are like this. You cannot intersect in some funny ways. So when you're tracing, if you're at the intersection, you might be in a little bit of trouble because you don't know which way to go. What you have to know, of course, is that if you have been going this way and you're going this way, when you see an intersection, you have to keep going that way. And if you're going up and down, then you have to keep going up and down. So how do we actually do this? Well, one of the things that you can check for when you're looking for the next place to go is to look and see if you're at an intersection, right? How do you know if you're at an intersection? You look at all four neighbors. If they're all X's, or and actually it's not just all X's, okay, it can be A's and B's as well. But in that case, if all of them are not dots, then you know you're at an intersection. And then if you remember which way you come, what direction you came in from, then you can just keep going. Okay, so that's another thing that you have to watch out for. So presumably what you would end up with would be basically all the borders identified as either A or B, and then you have to decide what are you going to do with the intersection, because maybe if you identified A first, then the B will override the A for the intersection. It doesn't really matter as long as you know which way it's supposed to be. Okay, so let's say like this, and so on. And now what you have to do is figure out how to count. Now you can easily count the borders, X, A, B, and then so on. So you know that you have R rows and C columns. Then the dots are basically R times C minus the number of A minus the number of P. But there are some dots that are outside, which maybe you don't care about. There's some dots that are just A, some dots that are B, and some dots that are A intersect B. All right. When I say you don't care about the outside, actually that's not completely true, because if you know the outside, if you know three of these things, you can get the fourth one just by subtraction. And the outside is actually relatively easy to get. Why? Because all you have to do is you start doing a first search from the outside. So maybe you would, what would you do? You would look at all the positions on the boundaries that are not a border. So for example, if this A is on the boundary, then you don't include it, but you include all of these dots that are on the boundaries, push it all into the queue to start a first search. And basically you just do a first search to fill all the things that are dots. And if if your neighbor is a dot, you keep going. If your neighbor is not a dot, or is visited, then you don't go. And by that first filling, you should be able to count how many things are outside. So that's the first thing, you figure out how many things are outside. So BFS from boundary. Now, when I say, okay, look at all the boundary things, and then whichever one it's not a border, you push it in BFSQ. Well, there's actually an easier way if you want. You can artificially introduce a border, so you make the field bigger, one on each side. So your actual state is always going to be it's going to be surrounded by empties. And then you can just do a BFS on one of the corners, and that should be good enough. All right, either way. The important thing is you can get the number of things outside by BFS from boundary. Okay, so now that you have marked all the outside, so we'll just, I don't know, mark it for something. Now you look for some other things that hasn't been marked yet. Okay, so now you look for something that hasn't been marked yet. And then you do a BFS from that. So the rest, you BFS from basically from a dot. Now, while you're doing BFS, again, you would visit all the unvisited things, and you would only go if then your neighbor is a dot. But if your neighbor is not a dot, then what are you going to see? You're going to see an A or B or both. Right? If you're here, yeah, I should be a little bit careful here because that's not going to help you. Let me think about how you're going to do just the A. So if you look for a place that is the dot and you're going to fill it, you're going to get a number. So you can find any of these dots and you can get three numbers. Actually, as I said, you can only need to do two of these because the third will be the outside, you can get it. And how do you know something is just A or something is just B? Let me think here. So while you are tracing the A's, you can keep a list of the coordinates in A, okay? And you can decide for particular coordinates if you want. You can either use bus fill or you can use something like point in polygon routine or whatever it is. You figure out whether this point is sitting in A or B or both. And once you have that, then of course when you flood fill it, then you know whether you are in which of these three regions you are. Again, you only have to do two of them because the third one is going to be basically the subtraction of the outside dots, the total number of dots minus the outside minus the two that you got inside. Okay, so that's basically how you can do this. It's not too bad. Okay, of course, there is a little bit of messiness, but conceptually it's not too bad. All right, now I want to look at probably the next one that next easiest problem is this wave until dark problem. Okay, so again, I'm not going to read through the problem statement, but I'll just quickly outline what this is about. So you have a bunch of kids. So you have kids, and there are at most n of them up to 100. And then you have some toys that also have 1 to up to m, again at most 100 of them. And then there's some toy category. And some toys will, each category will contain a certain number of toys. Some toys might not be in any category at all. And what you want to do is that some kids are willing to play with a certain number of toys. Okay, so some kid is willing, so maybe kid 1 is willing to play with a certain number, 1, 2, and 3. They did tell you that these ranges. So if it's okay, so sorry. These lines indicate that child J is willing to play with these toys. So they tell you which toys. So 2 might be only interested in playing with 4 and 6 and so on. Okay, so you have these kids can decide what toys they want to play with. And then the categories, so they're categories. Some toys may belong to category 1, and then some toys might belong to category 2, 3, and then there might be some toys that don't belong to any category. Okay, and what does it say? Toys can be, okay, so, and each category there's a limit on how many you can use. So for each category, at most R of these toys can be used. So you can't use more than R of them. Toys can be in at most 1 category, and any toy not listed in these P lines are not in any category at all, and all of them can be used. So I guess if you want, you can create an extra category. What category? I don't know, 0. Things that are not belong to any category, just put it there, and then you have a kind of an infinity. You can make R to be as big as you want. Okay, no toy appears. Okay, so display the maximum number of children that can be satisfied with a toy that they like, provided that each toy can be used by at most 1 child. So you cannot have 2 people sharing toys. So anyway, this is basically a standard assignment type of problem, right? So you're trying to assign kids to toys or vice versa. And if there wasn't this category business, all we are doing is the maximum bipartite matching. The fact that there's a category that limits how many of each type of toys you can use turns it into a little bit of a maximum flow problem. If you remember, if you have taken 3200 and we have this problem for counseling, this is very much similar to that. In that problem, I think there was like a student club for people, and then there's political parties, and you have to, each club can nominate 1 person, but then you don't want too many people from the same political party to be present. So that's pretty much the same problem. And the idea is that let me just go to the my board. So you have kids, you have toys, and you have categories. And basically, the kids would connect to the toys that they are willing to play with. And it's a standard maximum flow problem where we connect the source to each kid and give them basically 1 token. Okay, 1 token means they can use 1 toy. And then this token will be passed along to the toy. And there will be a outgoing edge to the category that has a capacity 1. The capacity 1 basically means that no 2 child can use the same toy. the toy can only be used once. Okay, and then as I said, there could be kind of a fake category, so the artificial category for all the things that don't belong to a category. And maybe there's another one here and so on. All of these are one. And then finally, to the sink, what are you going to do? You're just going to connect to the sink. Well, I'll just call it R1, R2 for the different categories. The limit of how many toys you can use from each category. So if this is 5, for example, that means that you cannot select more than 5 toys in this category. And that's it. Okay. Once you set up this graph, all you have to do is run maximum flow with your favorite method. Probably if you use the code library network flow number 1, or the one without any numbers is the right one. There are at most 100 bits, 100 toys, 100 categories. The number of nodes is at most basically 300 plus or minus a few with the source and sink and this artificial thing. And the number of edges, well, it's not that much because at the worst case, this layer has at most 10,000 edges if they're connected in all possible ways. And same thing here. Actually, no, because each toy can only belong in one category at most. So actually, there are only 100 edges. So the number of edges is not that high either. Okay, but also the maximum flow, the value of the maximum flow, it's also at most 100. So when you have a relatively small limit on the value of the final answer of a maximum flow problem, you want to use the Ford-Wilkinson algorithm, which is network flow.cc. Okay, basically the complexity there is the value of the flow, the answer, time, basically linear time. Okay, so that's pretty relatively fast. Anything more I have to say? No, I don't think that's anything more to say about this problem. Once you recognize that it's a maximum flow problem, and how do you recognize it's a maximum flow problem or some sort of assignment problem? Right, you have 3 types of things. They have some kind of connection, and there's the relationship between kit and toy. There's a relationship between toy and category. There's some kind of capacity, right? How many you can use for each category. So all that together really strongly indicates some kind of a maximum flow problem. Okay, the last one that I want to talk about. Let me erase this. The last one that I want to talk about is removal game. Okay, so removal game, you have a bunch of numbers up to 100. Okay, so they're up to 100 numbers. Each of these numbers will be up to 100,000. I might highlight things. Oh, I guess in math, this math can be highlighted. So each of these numbers is up to 100,000, 1,000. And basically the removal game is you pick in this 100 number, you start by removing some number in the middle. Or actually it could be the front or the back, doesn't matter. And the cost of removing that number is the GCD of the 2 numbers that's next to it. So when you remove one number, you will get 1 fewer. And you keep doing this until you have 2 numbers left. And then at the end, when he ends up with just 2 numbers remaining, he takes the GCD and adds that cost to the running total and ends the game by removing them both. So you basically just remove one number at a time. Every time you remove a number, whatever it's before and after, you take the GCD and that's the cost. And then at the end, when you have 2 left, you remove both of them by taking the GCD. And this thing is circular. So if you're the first element in the array, in the list, and you ask what is before you, that's actually the one at the end. Okay, so that's wrapping around either end if necessary. Okay, so and you want to find a way to remove every number to have the minimum total cost. Because depending on which numbers you decide to remove when, the total cost could be different. So that's basically what the problem is. Okay, so I'll just kind of say that you have an array of n numbers. This is what you're given, 0, 1, 2, all the way up to n minus 1. Okay, so I just put x as sort of some kind of number. We don't know what it is. And every time you remove a number, let's say you remove this one, then the cost of removing this is the GCD of this one, the one before, and the one after. And then this is gone. If you remove the first one, then the cost is the GCD of the next one and the previous one wrapped around. And if you remove the last one, then of course the same kind of situation. Okay, so that's the problem. And then when you manage to get down to the very end, you will have only two numbers left. Well, there's no removing something. You can't say what's the front and what's the one that's before and after. So when you only have two, you just remove both of them. And the cost of removing the last step is the GCD of these two things. All right. So that's the so the first problem, I guess, is how would you attack it, right? You can try to do, I guess, the exhaustive search, try all possible things to remove for the first step. Then you kind of delete that, you crunch it down, you compress the thing, close up that hole, and then you recursively try removing things with n minus one thing, right? We're solving the game with n minus one thing. But if you do that, then of course the first level you have n choices, and then each of the next levels, if once you remove the first one, the n minus one choices, n minus two, and so on, and you know where this is going. There's n factorial possibilities, the sequence of how you want to remove them, and of course that's way too much for n being what 100, right? 100, right? So no possible way. This will give you the right answer if you just look at all possible ways of removing stuff, but of course you can't do this. All right, so forget about that. Now the question then is there a way we can somehow when we do this recursion, right? We let's say we try this one and we remove it. Is there any way that we can save some? We see some collision of states that allow us to do dynamic programming. And you can look into this a bit. You can try things here and there, and as far as I know, I could not see it. So that's not very useful. But it turns out that the trick is to look at the problem backwards. So look at the end. The end, you have two numbers left. The problem is, where are these two numbers from? Could be any I and j, and in fact, because it's wrapped around, it could even be j and I. Okay, but I guess the order doesn't matter at the end. So it could be that this comes from here and that comes from here. We don't know which one, but we just know that they come from somewhere. So what we're going to do is we're going to just do basically n square loop to try all possible things with the last two elements. Okay, but why do we care about this? Why do we look at the last two? Okay, if you have the last two, if X, these two are really the last two that are left over, then what does that mean? That means somehow you have removed everything from I plus 1 to j minus 1, if you want to do inclusive indexing, and also from j plus 1 to I minus 1. So you have to be a little bit clever with the indexing to make sure that you have the wraparound taken care of. So somehow you have removed I plus 1 to j minus, so this sequence, and then you have removed, let me change the color. You have managed to remove this, and you have managed to remove this completely. So if you know how to remove a range completely, where the range is less length at most n minus 2, because we're never going to remove everything. We're going to remove everything except 2. Then we can solve this problem by basically saying that the cost, once if you decide what is I and j are the last two left, would be the GCD of AI and AJ, because that's the last step, plus the cost, which I'll just say F, of removing everything from I plus 1 to j minus 1, and the cost of everything from j minus 1 to I minus 1. Now, here you have to know that if the first index is bigger than the second index, it means there's a wraparound adjacent. But imagine that you have dealt with that, then that's what this is. Where F, AB, means cost of removing the interval from A to B. The best minimum cost, of course. And then when I write this interval again, remember that if A is greater than B, it means I wrap around. So now, basically what I do is I minimize, if I know how to compute f of A and B, then I just try all possible I and j of this thing, and then I'm done. And so the main mystery is how do I compute this? Okay, so let's look at that. Yeah, I'm not going to start a new page because apparently in my application, if I start a new page, it will often crash. All right, so how do I compute this f? So first of all, what are some easy cases? Like if I have I and I, right? If I'm just removing a single element, then that's actually the GCD of AI minus 1 and AI plus 1. Why? Because if I only have one thing, then I need to take the GCD of what's before and what's after my ring. Okay. What about in general? Okay, so in general, when I and say I are not the same, then we have to think about what's going on. So I have, okay, let me just undo this. Let me maybe remove this picture up here and redraw this. Now, yeah, again, I'm assuming for now that I is less than j. If I is bigger than j, then you have to do a little bit of detail work to make sure that you wrap around the right way. Okay, so we have I and j, and then we have something that comes before, which we'll call I minus 1, and something that comes after, which is j plus 1. But again, this could wrap around to the I minus 1 and j plus 1. So you have to take care of all of that stuff. All right, so anyway, the idea is that we're going to say, well, what is the last one that you remove in this range, I and j, from I to j? You're going to remove everybody except, well, you're going to remove them one at a time, but what is the last one? Maybe the last one is here, the last one that you remove. Well, if that's the case, that means you have to first remove, so this is at position k, this part, you have to remove this part, and then you have to remove this one. So to remove the last, these two ranges would be basically this. And then to remove the last one, the last thing that you remove would be the GCD of A I minus 1, A J plus 1. And of course, you're going to minimize this all over all possible K from I to J. Right? Because you don't know which one is the last one removed, so you're going to try them all. There is going to be a little bit of detail because if K is exactly I, then this first part is empty. If K is exactly J, then this part is empty, so you have to take care of that. That you only deal with the ones that are actually not empty. You might say, well, okay, if K minus 1 is if this is empty, then K minus 1 is less than I. Can I just check for that? Well, no, because we use that to indicate that the range is a wraparound. So you have to be a bit careful there. Alternatively, you can deal with the wraparound issue by just doubling your array. So just take the same array that concatenates itself twice. And then you can decide to, for example, start from here. And that means that you will never, if you're not removing I, right? So the smaller of the two things that you're going to remove the last is here, then you'll never, is it true that if you start from here, then you never have to worry about going backwards because you're never removing this one. Okay, you can just play this doubling trick if you wish to avoid the wraparound, and then that's just all the things that I said about before, or you can just do what I said at the beginning, which is to say that if the A is greater than B, you know that it's wrapped around. In any case, you have a recurrence. There are only basically n squared possible sets of input values for this function. So you just basically run a dynamic programmer with memorization, and that just solves the problem. And altogether, it's n squared, n3, and this part will be linear time. So altogether, it's n cubed time to compute this. Okay, so I think that's all I want to say for these three problems. And as I said, yeah, there are two other problems, A and J, which are not solved by many teams. You can look at it. A is a geometry with a graph combined to it, and then also the graph processing is not necessarily that trivial. And J is the kind of an exhaustive search combined with dynamic programming, combined with something else. So feel free to look at it if you want to ask me about this. Just reach out to me and we can talk about it. But if you can do all of the other 8 problems, B to I, that would already be very good. All right, so I think I'm going to stop here, and then next week we'll run another set.